Hey everyone, welcome to Linear Algebra. This is going to be lecture 1 of the course, and in this section we're going to basically kind of introduce ourselves to the sort of fundamental objects and operations of linear algebra, and those are vectors and the vector operations. And so we're going to kind of begin the course, obviously in a leisurely manner, but this is, even though this may be kind of review for a lot of people, particularly if you took Calculus 3, you may have come across vectors, or if you've taken a physics course or something, you've certainly seen vectors. We want to make sure that everyone's on solid footing before we start to drive into the more complicated areas of linear algebra. So we want to make sure everybody understands vectors well and that we're in a good place to go forward. So some of this might seem like review, but bear with it and just use it as use this lecture as a good review, if it is a review. So let's go ahead and jump into it. And so this will be section 1.1, and we'll just call it Fundamental Operations with Vectors. Okay, and so let's go ahead and start with what we mean by a vector. Start with a definition. And we'll say a real, and here we're going to use the term n vector to denote a vector with n entries. A real n vector is an ordered sequence of n real numbers. Okay. The set of all such vectors is denoted by this symbol, r to the n power. So Rn, this is typically just referred to as Rn, right? But this is the set of all real n vectors, okay, of dimension n, right? So for example, if we have vector 1 equals 1, 2, 3, vector 2 equals 0, 3, negative 4, and v4 equals negative 1, 0.25, and 2/3, then v1, v2, and v3 are all in what? R3. Okay, they're real vectors of size 3. They're real 3 vectors, you would say. Okay, and so they're all in R3. Okay, let's see. Two vectors. If given two vectors A and B, we say that A and B are equal. Two vectors A and B are equal if and only if all corresponding entries of A and B are the same. Okay. So, for example, if A is equal to A1, A2, ... AN, and B is equal to B1, B2, ... BN, then A equals B, right, if and only if A1 is equal to B1, A2 is equal to B2, and so on, AN is equal to BN, right? So all of the entries or components, if you like, are identical. Okay. And then another thing we'll need here at the onset is the idea of a scalar. So when we talk about a single number, it's usually called a scalar, right? To distinguish it from a vector, right? So like if I have the number 10, you maybe could think of this as a one vector, real one vector if you want, but 10 is usually called a scalar. Rather than a one vector, right? So I mean, technically you might be able to say that it's a one vector, but it's things like this, individual numbers are typically referred to as scalars. Okay, perfect. So vectors, what's a vector? Some notation, R3, what do we mean by that? When are two vectors equal, and what happens in the case, the sort of base case of an n vector where n is equal to 1, we call that technically a scalar rather than a vector. Let's move into something more concrete. Let's talk about vectors in R2. So vectors in R2 represent movement from one point to another. Okay, so let's put some vectors in the plane here. And let's draw a vector here at, so we've got this vector here, right? So this is the point 0, 0, and this is the point 2, 4. So this will be V1. So V1 is the movement, can be thought of as the movement from 0, 0 to the point 2, 4 in the plane. Okay, what about if I start with a vector that's out here a little further? 1, 2, 3, 4. Let's put one up here at 3, 5. A point at 3, 5. And then let's put a point at 4, 5, 6, 2. Let me put this guy here. So this would be a vector as well. We can think of this. If this is vector v2, then we'll say v2 is the movement from 3, 5 to 6, 2. Okay, right? Now in this case, because the tail of the vector is not at the origin 0, 0, if we really wanted to write v2, what we would have to do is do something like this. We could subtract the the ending point from the starting point, and we would get that vector there. Okay, so the point of this is just to say that vectors in two-dimensional space have definite and clear interpretations, right? You can think of them as movement from one point to another. You could obviously expand this idea to R3 as well, right? It would have a similar interpretation, but it would just have the additional dimension, right? So instead of just xy axes, you would have xyz axes. Okay, so a little bit of just kind of some background, some geometric background. Some of this stuff will come up as we start to work through the course. We'll start to develop theorems and develop definitions and whatnot in general, but then we'll want to be able to use vectors for specific applications in two-dimensional space or three-dimensional space, and just having some sense of how these things can represent movement will be important when we get there. Let's talk about the length of a vector. What do we mean by the length of a vector? So the length, also known as the norm or the magnitude, right? Depending on the application or the context. I think norm is probably the most typical way we refer to this, but length is certainly probably the most straightforward way to say it. So the length or norm or magnitude of a vector And we'll say the vector is equal to a1, a2, dot, 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 an, so an n vector in Rn. Right? How do we define the length of the norm? Well, it could be denoted like this, right? And it's basically going to be the sum of the squares of the components. So you square the first, square the second, so on, add them all up, and then take the square root. That's what we mean by the norm of a vector, or the length of a vector. Right? And you can clearly, if you think about this in two-dimensional space, right? This is the Pythagorean identity. Well, the Pythagorean theorem. Right? If I have some line, right, and I want to know the length of the line between 2 points, then I can identify a right triangle, right, built off of that line. And this we sometimes call x, and this we sometimes call y. And so if this is a, then we know a squared equals x squared plus y squared. And so a, the length, is equal to the square root of them. Right? And so this is the Pythagorean theorem at work, more or less. Right? And so this is just a kind of a more generalization of that. You basically have the sum in 2 dimensions would look just like the Pythagorean theorem, but then if you have additional dimensions, you just add them to the radical. Okay. All right. Let's do an example where we find the norm. Let's do an example of this. Find the norm of v equals 1, 3, negative 2, 0. Okay, so the norm we know is just equal to the square, the sum of squares of all the components. So that's 1 squared plus 3 squared plus negative 2 squared plus 0 squared. Take the square root. So that's 1 plus 9 plus 4 plus 0. And so this is the square root of 15. Okay. And so notice naturally that in this case the norm was positive, and in general the norm has to be positive. So the norm is always non-negative. You can't have a norm that is 0 technically as well. Right? But this would make sense if we think about the vector as having a certain magnitude or a length. We don't usually like the idea of a negative length. Right? Lengths are always positive. And so the norm is always positive. Okay? Pretty straightforward so far. Let's talk about, so if I have a vector whose norm is 1, that vector has a special name. So any vector of length 1 is called a unit vector. Okay, a unit vector. Okay, and so an example here would be in R2, v equals 3/5, comma, negative 4/5 is a unit vector. How can we see this? Well, you could take the norm of v. Oops. You could take the norm of v. Right, so 3/5 squared plus negative 4/5 squared, square root of that. What are you going to get here? You're going to get 9 over 25 plus 16 over 25. So that's 25 over 25, and the square root of that is square root of 1, so it's just 1. Right, so you can see that the norm, the length of v is 1, so v is what we call a unit vector. Okay. Very good. Okay, and given these unit vectors, there are a handful of, well, depending on which space you're in. If you're in R2, for example, there are two special unit vectors, which we call standard unit vectors. So the standard unit vectors over R2 are 1, 0 and 0, 1. And so these have special denotation. These are denoted by an I or a J. And so frequently they'll be written like this: I hat equals 0, 1, and J hat equals, sorry, that's exactly backwards. This is 1, 0, and J hat is equal to 0, 1. Right, so this is the unit vector that kind of is associated with the x-axis, x direction. This is the unit vector that's associated with the y direction. And so the I and J just kind of have developed for whatever reason. In R3, there are 3 standard unit vectors. Right, and they all have names as well. So you've got 1, 0, 0 for I. For J, you've got 0, 1, 0, and then there's a third one, which is called K, and that's 0, 0, 1. Okay, and so these are the standard unit vectors in R3. Now in R4, how many standard unit vectors are we going to have? Well, we're going to have 4 of them. They aren't going to have nice names anymore, but you've got 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Right, so those are the 4 standard vectors in R4, and so on. Right, so the nth standard vector in Rn is going to be all zeros except for the nth position. We'll have a 1. Okay. All right, very good. Very good. So a lot of definitions here, just kind of trying to lay the groundwork, and then we'll start to combine some of these ideas and build on them. Let's see. Let's define scalar multiplication. Oops. Okay. So let's let x equal x1 through xn, right? And this is obviously a vector in Rn, real valued vector. And let c be a real number, i.e. a scalar. Okay, so we've got an n vector in Rn, and we've got a scalar, right, a real number. Right, so then we have what's called scalar multiplication. Okay, scalar multiplication, it looks like this. So if I want to take c times x, and so maybe I should denote x as a vector with the vector symbol on top just for now. We may switch off of that, just to distinguish x from its components and to distinguish the vector from the scalar. Right, so if I want to multiply a scalar times a vector, then just kind of thinking this through here, what does this look like? Well, what ends up happening is it's kind of, you basically take the scalar and you multiply it by each component separately. Right, so this is going to be equal to c times x1, and then c times x2, and so on, all the way up to xn. Okay, and this is what we mean by scalar multiplication. Okay, let's do an example. Let's let x equal 1, 2. Okay, then what's 2x? 2x is equal to 2 times 1, 2, which is 2 times 1 is 2, and 2 times 2 is 4. Okay, what about 3x? Well, that's 3 times 1, 2. All right, so that's equal to 3 comma 6. Okay. And what does this do? What are we doing to the vector? Since we're in R2, we can think about this. What is the geometric sort of meaning of this? Well, the vector started out at 1, 2, right? So it was like this. Okay, so this would be just x. And when we multiplied it times the scalar 2, it became 2, 4. So now it looks like this. So this would be 2x. All right, and then obviously if we multiply it by 3, it went up to 3, 6. Okay. And so it's important to notice here that when we write the vector x and 2x and 3x, what we really mean is this. So here we've got x, right? And here we've got the vector 2x, right? And here we maybe have the vector 3x, right? And so, and this, sorry, that should be just over the x. But we are not talking about the points, right? We're talking about the directed line segment that starts at the origin and ends at some point. Okay, and it ends at the point in this case of 3x, 2x, or sorry, 3, 6, 2, 4, and 1, 2. Okay. All right. So that's scalar multiplication. Okay. Let's take a look at our first theorem then. This will be our first theorem. Okay, and so what do we got here? Let's let x be an Rn, so this is a vector in Rn, and let c be a real number. Then the norm of c times x is equal to the absolute value of c times the norm of x. Okay, so what this is saying is if I take a vector and I multiply it by a scalar and I take the norm of the new vector, cx, that's going to be the same as taking the norm of the original vector x times the absolute value of c. Let's see if we can prove this. Should be relatively straightforward, right? So let's try to prove this. So we'll just start with this and we'll derive this. So we'll start over here and we'll see what happens here. So the norm here, we know that this is going to be equal to the norm of c times x1, x2, xn. Right, and we know what the scalar multiplication means. That means you've got cx1, cx2, cxn. Can we take the norm of this vector? Sure. cx1 squared plus cx2 squared plus plus cxn squared, and we need to take the square root of that. Okay. Now inside here, each of the terms inside this radical can be squared separately, right? So you have c squared x1 squared plus c squared x2 squared plus plus c squared xn squared. Right, and so we can factor out the c squared here. And we just have x1 squared plus x2 squared plus plus xn squared, like so. Right, and then we could think of this as the square root of c squared times the square root of x1 squared plus plus xn squared. Right, just basically kind of break the radical into two pieces. Now, if I start with a c that's negative and I square it, it becomes positive, and then if I take the square root, it remains positive, right? But I'm back to the same absolute value as the original c, right? And so the act of squaring and taking the square root is equivalent to identifying the absolute value. So this is equal to the absolute value of c, right? And this is just the norm of the vector x, right? And that's exactly what we were trying to get to, right? So that gets us where we need to go. Okay. Perfect. All right, let's keep moving forward here. Now, we'll frequently want to talk about vectors being in the same direction. So what do we mean by two vectors being in the same direction? Let's define that concept here. So two vectors, x and y in Rn, okay, are in the same direction they're in the same direction if and only if, right? If and only if there's a positive real number c, a scalar c in R, okay, such that y is equal to c times x. Okay, right? So hopefully that's kind of straightforward, right? Because we saw what happens with scalars of vectors, right? We saw when we had x was 1, 2, and then 2x was 2, 4. Basically, the vector just gets longer, doesn't it? But it remains in the same direction, right? And so if a vector is in the same direction, if two vectors are in the same direction, then it should be possible to scale one of them to the length of the other. And that's what this is saying. That's what this is basically saying. And similarly, two vectors are in opposite directions. Right, they're in opposite directions if there is a, well, so this should say positive here. Let's put R plus. Okay, if there is a scalar c in R minus, so a negative real number, such that y is equal to cx. Okay. Right, and so two vectors are in the same direction if you got a positive value for the constant or for the scalar, and they're in the opposite directions if c is a negative number. And two vectors are called parallel if they're either in the same direction or opposite directions. Okay, same direction or opposite directions. Now, kind of a quicker way to say that would be to say there is a scalar c in R, positive or negative, such that y is equal to cx. Okay, so that's what we mean by in the same direction, or in opposite directions, or parallel. So we kind of define three things there, very tightly related, obviously. So let's take a look at some examples here. So if I have x equals 1, negative 3, and y equals 3, negative 9, these are in the same direction. Right, and they're in the same direction because x is equal to, 3x is equal to y. Right? Right, so basically you can see here that 3 comma negative 9 is equal to 3 times 1 comma negative 3. Okay, what if I have a different xy? What if I have x equals 1, negative 3 again, and y equals negative 3 comma 9. Well, what happens here? Well, these are in opposite directions. Right? And here you can see that it's negative 3x equals y. Right? So 3 comma negative 9 is equal to negative 3 times negative 1. Sorry. So negative 3x is equal to y. Right? And that's because negative 3 times negative 3, 9. Right? This guy here, y, is equal to negative 3 times this. Right, so the negative 3 times 1 gives you the negative 3, and the negative 3 times negative 3 gives you the positive 9. So the negative flips the direction of this vector. All right. Right, and then obviously all three of the vectors given are parallel. Right, so negative 3 comma 9, 3 comma 9, negative 9, and 1 comma negative 3 are all parallel. Right, because of these various c's that can be chosen to make them align. All right. All right. So, here is kind of a quick corollary. If x is a non-zero vector in Rn, then u equal to 1 over the norm of x times x is a unit vector in the same direction. Okay, so if you've got some vector x and you want to normalize it, then you can just multiply it by the reciprocal of its norm. Okay, so let's prove this. This is a simple proof that uses what we just talked about. So u is equal to 1 over the norm of x times x is equal to c times x. Right, so this is a constant, right? 1 over the norm. The norm is always just a real number, right? So this certainly is a constant, right? So if u has this form, then u is certainly in the same direction as x. Right, because u is equal to cx and c is a real number. Okay, now how do we know that it's a unit vector though? Okay, how do we know it's a unit vector? Well, I guess we know that so it's in the same direction, yeah. So how do we know it's a unit vector? All right, let's take the norm of u, and if we can show that the norm of u is equal to 1, then we've got a unit vector in the same direction. So how do we know u is a unit vector? That's kind of the part 2 of this guy. So if you take the norm of u, then that's equal to the norm of 1 over the norm of x times x. Right, and so what do we get here? Well, this is just a scalar, so that can come outside. We know it's the absolute value of this thing. Okay, and so the absolute value of 1 over the norm, they're both positive. So this is 1 over the norm of x times the norm of x. Well, and you can see what happens. You get this nice cancellation, and you just are left with 1. Right, and so u is a unit vector in the direction of x as intended. That's what we wanted to see. Okay. All right. Let's do an example where we use this. This will come in very handy throughout the course. We'll be using this stuff. We'll be calculate a unit vector in this certain direction, blah, blah, blah. That kind of thing will come up all the time. So let's calculate a unit vector so let's calculate the unit vector u in the same direction as the R4 vector 2, 3, negative 1, 1. Okay, so first thing we need is the norm of this vector. Right, and that's easy to calculate. It's 2 squared plus 3 squared plus negative 1 squared plus 1 squared. Take the square root of that. And this is 4 plus 9 plus 1 plus 1, so you get square root of 15. Okay, so that means u is equal to 1 over the square root of 15 times the vector itself. When I say times, I mean scalar multiplication. Right, so you could write it like this. This is fine to leave it like this. You could also, kind of do it like this if you want to. Just emphasize that this is the vector. All right. Okay, so I've got this guy here. And so this is going to be a unit vector in the direction of the given vector, 2, 3, negative 1, 1. Obviously, when you scale it down to have the exact length of 1, frequently the components of the vector will sort of take on a less than they might be more complicated types of numbers, like 2 over the square root of 15, for example. But that's okay, because all we needed was a vector that was a unit vector in the same direction, and that's what we now have. Okay. Excellent. Excellent. Let's take a look at our first laundry list kind of theorem. Okay, so this is a theorem with many parts. Okay, and this is just going to bring in a lot of the features of algebra, the properties of algebra that we're largely familiar with, but maybe we're not familiar with them in the context of vectors. And so we're going to kind of redefine all this stuff here. So let's let x equal x1, x2, xn, and y equal y1, y2, yn. And z, we'll need 3 of them, equals z1, z2, zn. Be vectors in Rn, right? So n vectors, real valued n vectors, and let c and d be scalars, so real numbers. Let's let the 0 vector equal the vector that has n entries, all of which are 0 in Rn. Then, what do we have? Well, we've got about 8 items to look at. So let's see. The first one is the commutative law, which says that if I take 2 vectors and I add them together, the order does not matter. Right? And this is the commutative law of addition in particular. Right, so we've got the commutative law of addition, which we're certainly familiar with. 2 plus 5 is the same as 5 plus 2. Well, it turns out that's true for vectors as well. We could easily prove this. Maybe we'll prove this one. We'll prove a couple of these, not all of them. It just takes too long. There's also this. If I take a vector x plus 2 vectors y and z, then it's the same as adding x and y first and then adding z, right? And this is associative law of addition. Important to say that of addition piece because these all both have associativity for multiplication and commutativity for multiplication. Okay, and so that's that one, right? So 2 plus 3 plus 4 is the same as 2 plus 3 plus 4, right? It's the same idea, same principle here. The identity element of addition, right? So if I take 0 vector plus any vector x, then I get the same thing as x plus 0, and both of those are equal to just x, right? This is what's called the identity element of addition, right? And this will mean more, well, I mean, we'll talk about this somewhat, the identity element, but this is an extremely important idea when you get to abstract algebra. Linear algebra, we certainly make use of it, but it's not as central as it is in abstract algebra. But this is the idea that there exists some vector that's a 0 vector such that when we add it to anything else, it doesn't change the vector that it's added to. Okay, kind of similar in idea is the inverse element. And so x plus negative x is equal to, it's equal to basically negative x plus x. And what do you get? You get the 0 vector. This is called the inverse element for addition. Okay, so the inverse element is another idea, again, very important in abstract algebra. We'll use it for sure here, but it doesn't become as it's not as central to linear algebra as it is to abstract algebra. And then there's the distributive law, right? If I have a scalar and then I have two vectors x and y which I'm adding together, then I can separately do the scalar multiplication for each vector and then do the vector sum, like so. Right, so I could add the vectors together first and then do the scalar multiplication on the sum, or I can do the scalar multiplication separately for each vectors and then do vector addition. This is the distributive law. Okay, very good. And there is another version here. If I have two scalars that I'm adding together and I want to multiply them by this vector x, then I can do something similar to the distributive law up above, but here I've got two scalars and one vector. But up above I had two vectors and a scalar, right? But this would be equal to c times x plus d times x. Okay, this is again the distributive law. And sometimes people refer to this as multiplication over addition. Okay. And another version of associativity, but for scalars, is if I have two scalars, I multiply them together, and then I do a scalar product, or scalar multiplication, then that's the same thing as first doing the scalar multiplication with the vector and then multiplying again with another scalar, right? So here I've got two scalars multiplied together will give me a scalar times a vector. Here I've got a scalar times a vector gives me a vector, and then a scalar times a vector, right? And so this is another version of associativity. Okay. And then the last one is the identity property for multiplication. So if I have a vector x and I multiply it by the scalar 1, then naturally that leaves me with just x, right? All right, so this is identity. This is the identity property. For scalar multiplication. Okay. All right. Most of these are relatively straight. Most of these are straightforward. Let's prove one of them. Let's take a look at how about like number 6? How about this one? Okay, let's prove number 6. Right, so let's look at 6. So what we can do here is we can say, okay, we'll start with just c plus d times x. Well, what is that? That's c plus d times x1, x2, dot, 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 xn, right? So c plus d, those are scalars, and this is a vector, right? And so first thing I can do is just distribute the sum, the scalar sum, throughout the expression, right? And so when I do that, I would have c plus d times x1, c plus d times x2, dot, 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 c plus d times xn, right? So just kind of distributing that scalar through all of the components of the vector, right? And then you can obviously see at this point, these are all real numbers. So c is a real number, d is a real number, x1 is a real number. These are real valued vectors, and these are the components. So when I get down to this level, then it's just cx1 plus dx1, cx2 plus dx2, and so forth. Right, so I get this. Right, and then so what I can do here is I can separate out the two vectors. This looks a lot like just a vector sum, right, where you've got two vectors that you're adding together. Right, so let me write that. This is just a vector sum. And what are the two vectors in the sum? Well, you've got this guy here, which is cx1, cx2, dot, 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 cxn, and then the other vector is the dx vector, dx1, dx2, dxn, right? Okay, and then this is just c times x, and this is d times x. Okay, and so that's exactly what we wanted to show. Right, so that's exactly what we were after. Right, and so that's an example of how a lot of linear algebra proofs kind of follow this sort of idea, right? You take the thing that's given. They're what are known as direct proofs. So you start with what's given, and you just expand or contract the thing, rearrange it a little bit, and then you get to the other side of the equality statement, right? So if such and such equals such and such, you start on the one side, do a bunch of stuff to it, expand it. Typically in linear algebra, what you'll like to do is like write the vector in its component form, distribute, expand, rearrange, and then you'll see, oh, in fact, it could also be written in this form now, right? Which is kind of what we did here. And a lot of the other 7 properties that we just looked at, they all follow kind of the same pattern. So I'll just say the other 7 all follow this same pattern. Right? Started with the one side and derive to the other side. Okay? All right. Very good. Here's another theorem. Okay, so we've got some definitions. We've got some things to talk about. So naturally, theorems will start to arise as we combine the things and flesh out their properties. So let's let x be a vector in Rn, and C a scalar, real value, real number, right? So if C times X is equal to the 0 vector, then either C is equal to 0 or X is the 0 vector, right? So what this is basically saying is if you have a scalar and a vector and you multiply them together and the product is the scalar product, the scalar multiplication results in a 0 vector, then either the scalar is 0 or the vector is 0. There's no other option, right? So this is going to be important, obviously, for what comes forward. Like, we'll need to be able to know when a scalar multiplication results in a 0 vector. We need to be able to know that when that happens, either the scalar is 0 or the vector is a 0 vector, right? So let's prove this. So let's assume that C is not equal to 0. All right, we'll start with that, and we'll show that X must be 0. Okay, so we'll do it this way. Start with this one, right? So if C times X is equal to the 0 vector, that implies that C times X1, C times X2, C times Xn equals 0, 0, ... 0, right? So that's what we mean. Okay. And so what follows? Well, if these two vectors are equal, then this component has to equal that component and so forth, right? So Cx1 equals 0, Cx2 equals 0, Cxn equals 0. So all of the products inside the vector now have to equal 0. And since C is non-zero, by assumption, that's going to imply that x1 equals 0, x2 equals 0, xn equals 0, right? Which obviously implies that x equals the 0 vector. Okay, so we've just shown that if C is non-zero, but C times X is equal to 0, then X must be 0. Now let's do the other one. Right, so we've shown the one direction, right? So next let's assume that X is non-zero, not equal to the 0 vector. And we'll show that C is equal to 0. Okay, so let's see here. Similar, let's start in the same fashion. Let's say C times X is equal to the 0 vector. Okay, so that implies that Cx1, Cx2, ... Cxn is equal to 0, 0, ... 0. Okay, and so that's going to imply that, right? So Cx1 is equal to Cx2, which is equal to ... which is equal to Cxn, all equal to 0, right? Now, we know that X is non-zero. We know that X is not equal to the 0 vector. That's by assumption, right? And what does that mean? Well, that just means that some xi is non-zero. Maybe all of them are non-zero, but maybe only one of them is non-zero. Okay. And so what does that imply then? So if some xi is non-zero, right? Let's just assume xi is non-zero. That means C times xi equals 0 implies C must be equal to 0, right? So if my ith term C times xi is equal to 0 and xi is non-zero, then clearly C must be 0. And so if C is 0 for any one of these terms, it must be 0 for all of these terms. So C is equal to 0, right? And that's all we need to show. Okay, Perfect. Right, so we've shown it kind of both directions. And so now we should be able to say, yes, if I've got a scalar multiplication resulting in the 0 vector, then either C is 0, either the scalar is 0, or the vector is 0. Okay. All right, excellent. Excellent. Okay, making good progress here. And let's have one more definition and a couple of examples, and then we'll call it quits for this first introductory lecture. Okay, we'll start with this definition of what do we mean by a linear combination. So let's let V1, V2, Vk be vectors in Rn. Okay, these are n vectors. There's k of them. So then we say, then the vector v is a linear combination, right? It's a linear combination of v1, v2, vk, if and only if there exists scalars C1, C2 through CK in R such that the vector v is equal to C1 times V1 plus C2 times V2 plus ... plus CK times VK. Okay, so V is a linear combination of these k vectors if and only if I can find a handful of scalars such that I can do the sum product here. Okay. Linear combinations are going to play an enormous role in what's to follow, so it's a good idea to make sure you get kind of a clear sense for this at the onset here. Let's do an example. Okay, so the vector -2, 5, 8, 5, 0 is a linear combination of a couple other vectors, three other vectors in particular, of 3, 1, -2, 2, 1, 0, 3, -1, and 4, -2, 1, 0. Right, and so this vector here is a linear combination of these three. And why can we say that? Because why? Well, because I can find scalars such that I can add I can create a sum product to give me this vector here. Right, so in particular, I can use 2 times the first one, 3, 1, -2, 2, plus 4 times the second one, 1, 0, 3, -1, plus -3 times this third one, 4, -2, 1, 0. Right? And so what do I get when I do it? Let's add these all up. So I get, what happens here? 6, 2, -4, 4, plus, and just multiplying the scalars through here, 2 times 3 is 6, 2 times 1 is 2, etc. And here I have 4, 0, 12, -4. And then I have -12, 6, -3, 0. Right, and if I add these three vectors together, what do I get? Well, 6 plus 4 is 10, plus -12 is -2. 2 plus 0 is 2, plus 6 is 8, right, and so on. Right, so if I add these together, I get this guy here, which is that guy there. Right, so there exist scalars such that I can create a sum product with three scalars and these three vectors to create the original vector. Okay, so that means this vector is a linear combination of these three. Okay, very good. And one more example. this one will be very helpful. Any vector in R3 can be expressed as a linear combination of I, j, k, standard unit vectors. Okay, so for example, if I take the vector 3, -2, 5, that's equal to 3i plus -2j plus 5k. Right, and let's see what does that look like. So that's 3 times 1, 0, 0 plus -2 times 0, 1, 0 plus 5 times 0, 0, 1. Right, and so I know that's 3, 0, 0 plus 0, -2, 0 plus 0, 0, 5. And of course, that gets me 3, -2, 5. 3 plus 0 gives me 3. 0 plus -2 plus 0 gives me -2, and so on. Okay, so obviously the same thing is true in R2, just using I and j. I can represent any vector in R2 just using I and j. And it turns out that, you know, any vector in Rn can be represented by using n standard unit vectors from Rn. Okay. All right, and so we'll get into more of this next time for sure, but that's a great place to leave off with this one. So when we come back next time for the next lecture, we'll get into what's something called the dot product, which is a very important type of multiplication, type of product that exists for vectors. A little bit of review, if you've taken calculus 3, you'll have seen the dot product. But we'll get into it in quite a bit more detail in the coming lecture than we did in Calc 3. So, all right, take care, and we will see you all next time.